So in this presentation, we're going to look at filters, which is a combination of chapter 5 and 6, RC circuits, RL circuits, and a little bit of RCL circuits. And then at the end, we're also going to tie this back home with some op-amp circuits and how to filter those out as well. So in this first slide, we're going to look at, again, this is a slide that we used previously about sinusoidal signals. And this is the equation Vt equals Vm sine omega t equals Vm sine 2 pi ft. Because remember, omega equals 2 pi f. And so this is just showing, again, the basics of a signal and how it's formed using your sine wave, using your amplitude of Vm, and using the omega or 2 pi frequency. Furthermore, it's showing you what the shift of phase does, and the time shift delta t, which is shifts your signal starting point from left to right based upon how large it is. So an RC circuit can be a low pass and a high pass filter, and here we're going to look at it in a voltage divider configuration because we did a lot with voltage dividers in chapter 3. So in this, we have an impedance form of the voltage divider. So right here we have a basic slide that we looked at previously in chapter 3. We have a voltage source and we have two resistors next to it. And instead of doing the resistors by R, we're going to measure them by impedance Z. And so we can use the same circuit to create the voltage divider for resistors. And you can see that the gain equals V out over V in equals R2 over R1 plus R2, or the total of the two. And that V out is over that second resistor, that lower resistor there, V out. You can see in the picture in the top left. So this is going to give us our, essentially our gain, our V in versus our V out. However, we can do more than this than just resistors. So a resistor's impedance is its resistance. ZR, which is the impedance of the resistor, equals R, or the resistance in ohms. However, we can also use the same model for the impedance of an inductor and the impedance of a capacitor. And the equations for the impedance of the inductor and capacitor are given in the bottom middle and the bottom right. And that's saying the impedance of an inductor equals j omega L, and the impedance of a capacitor equals 1 over j omega C, where C is the capacitance and L is the inductance. So we can use that same form that is above for gain equals output over input, V out over V in. And instead of the R's that we previously used in chapter 3, we're just going to put Z's because that's the impedance. And we can substitute then in any one of these other two impedances, impedance for an inductor or impedance for a capacitor, in order to find the gain of that system. So here we have a picture of a voltage source. We have our resistor, and then we have our capacitor after that. And we're asking what is the voltage V out, V over the capacitor. And so what we can do is take our gain equation, which is our V out over our V in. We can substitute it in with the voltage divider equation, Z2 over the sum of Z1 and Z2. And then we can substitute those in for our capacitor and our resistors. So our impedance of our capacitor over our impedance of our resistor plus capacitor. And then we can substitute the equations in for the z's. And remember, z of a capacitor equals 1 over j omega c, z of a resistor equals r, and z of a capacitor equals 1 over j omega c. And that's going to be able to give us, if we multiply out, that's going to give us our equations for gain for a resistor and capacitor circuit. And so here you're going to be able to see our V0 over VI is going to equal those two equations there. Either form of them works well to be able to get to the gain of the system. So the interesting part, though, then is what do we do with J? How do we deal with it? So if we look at these, we know it's 1, we know 1 because it's a constant. We have J, we're not really sure what that is. We have omega, which equals 2 pi frequency. We have our R, which is our resistance in ohms, and our capacitance, which is C in farads. However, that J, we're not really sure what it is. So we're going to look in the next slide at what J means. So J, again, we can, comes from Euler, and there is an identity. So E up to the IX equals cosine X, I sine X. And we can define J as part of the complex number having a real and imaginary part, and the J is the imaginary part. So based on this, we can view this as a vector. So we take our A component of our vector and we plot it on our x-axis. we take our b component of our vector and plot it on our y, going up y-axis wise, and then we can get our magnitude of the new vector, which is a squared plus b squared square root, and then we can also get our phase angle of the new vector, which is arctan b over a. And so that angle is giving us the angle off the x-axis that magnitude vector reaches, and the magnitude of that vector is the c again that we just found out. So essentially, this is how we can make that j, which is essentially that complex number, into a real and an imaginary part, and then calculate things based upon it. So again, we have the same sinusoidal signal here. We have our 2 pi f. If we look at our Vm, that's going to be our amplitude, and we have our phase value there. So if we go back to the previous slide and look at it, you can see that the magnitude that we got out of that c equals the square root of a squared plus b squared, that can translate into your amplitude. And then the phase angle, which is the arctan of b over a, can translate into the phase. And that's how we can pull one of those previous equations into the wave equation here. Here we have an RC circuit as a low-pass filter, which means it lets low frequencies pass, which are the slower, more oscillating signals. It does not let high frequencies pass, or ultra-high frequencies, or any other. So it's a low-pass filter, low passes. So this is an RC configuration low pass. So we have a voltage source, we have our resistor, and we have our capacitor after that. And we're looking at the voltage drop over that capacitor. And so what we got here is we have our gain equation that we had previously, G, the absolute value of G, and we've solved in for the voltage divider equation for those impedances based upon the impedance values of capacitors and resistors. We've done a little bit of trig in that middle, a little bit of algebra in that middle one to cancel like terms. And then in the bottom, we've got our gain equation, V out over V in equals 1 over 1 plus j omega RC. So now we have to be able to convert that omega into 2 pi times the frequency. And remember, if we're looking at c equals a squared plus b squared, we can also convert out that j as well in order to simplify the equation further. And that's why we've got that square root over the sum of the two squared inside of there. That's how we get the c out. So this is going to give us our total gain equation based upon numbers that we have access to. So we should have 2 pi as a constant, the frequency should be given, the resistance is given, the capacitance is given. So every number in that is given, therefore we can calculate our gain equation for this. So another thing that's important, RC circuit as a low pass filter, we have to define what low pass means. And so in definition, we use something called a cutoff frequency. And the frequency of the cutoff for a low pass filter equals 1 over 2 pi RC. Or the omega c of the low pass, or the omega cutoff of low pass, equals 1 over RC. And so this is a defined a definition that we give in order to say what is low frequency and what is not low frequency. Where does the cutoff happen? Where does it start cutting off those high frequencies? So if we look at plotting this, we look at the frequency of the cutoff of the low pass filter is the point where the output is reached by 1 divided by the square root of 2, or so we look at that. So 1 divided by the square root of 2 is 0.707. So we're going to go right on that. We're going to look on the y-axis for the 0.7. And it's a little bit above that. We're going to trace that over, and we're going to see that the frequencies that get cut off are around 1,100. So anything above 1,100, we're really going to start hammering off and cutting off. Anything below that is a low frequency, and that's where most of it is going to attenuate through our circuit. And so we can further calculate these off. And this value is a selected value, so you'll see 1 over square root of 2 a couple times in this course as your cutoff range. But for the frequency cutoff for a low-pass filter, that's what we're looking at. And so next question is, how much of a frequency are we cutting off after there? What percentage of the frequency are we cutting out? Because obviously that x-axis is frequency, so we're looking at 1,000 hertz, 1,100 hertz, 1,100 times cycles. So what does that mean when we're saying at that point we're going to cut it off? We're going to look at the next slide. So here we're going to look at our frequencies versus our attenuation. So how much quieter you can think of they are, because on the y-axis we're looking in decibels for the unit, and the x-axis we're looking at frequency. So from the previous chart, we've looked at and found the frequency at around 1,100. So in this chart, we can look at the attenuation of that frequency. And so if we drag over exactly on that point, so 1,100 as the frequency, if we drag over to that y-axis, we can see that's at about -3 decibels. So the frequency, the cutoff frequency for the low pass filter is at 3 decibel point. So remember, decibels is a logarithmic increasing scale. So these numbers, this isn't a logarithmic graph. So therefore, every single value as you get lower on that decibels is increased cutoff. So essentially, the signal is getting increasingly quiet as we go up through frequencies. It's not linear. And so anything to the left of that, you can see it's less than 3 decibels, which isn't that much of a cutoff. If you look right around 100 as the frequency, 100 hertz, you can see that there's almost no cutoff between, like, what is that, 50 and maybe 500. That's a very, very quiet cutoff. But if you look at anything above 1,100, you're going to see that frequency is being attenuated very, very quickly. It's being cut off very, very quickly and not allowed to pass through the circuit. So here we have an exercise RC low pass filter that we'll solve in class. And here's our equations that we need. Using a 3.3 mu f capacitor, design a low frequency filter with a cutoff frequency of 75 hertz. So again, we can use that equation on the right to look at what resistance value we need, because we have the frequency, we have our R, we have our C, and so we can use that to calculate out our values. So then we can use the gain to calculate out what our gain is for this circuit. So our gain at the cutoff frequency, we already said, is 1 over square root of 2. And the gain in decibels at our cutoff frequency is -3 decibels, which is a standardized answer. Well, that is the answer of what this is. And so then we can look at the gain of this filter at 150 hertz. And that's saying if I take this previous filter and I don't change anything and I just plug 150 hertz into it, what is the gain of that? And we can substitute that out and solve to be able to get the gain of that system. And then we can look at the gain of this filter in decibels at 150 hertz again, and we can solve through. So the gain is 0.4477, and the gain in decibels is -7. And then finally, for an input value of V in equals 10 sine 2 pi 150t, which is a signal that's coming in, what is the output of the circuit? And we can just use our gain times whatever that equation is there, and we can get 0.477 times 10, and that gain is 0.477, because remember, that's the first part, Vm, of the waveform that we looked at in slide number 1, the first slide that we looked at today. So you're taking that 0.477, you're multiplying it by that function, that constant in front of that function of sine, that sine function. That's going to give us our total voltage out at that point. So here we have another quick example. We have our RC low pass filter. We have our resistance of 2,700 ohms, a capacitance of 3.9 mu farad. We have our Vn of 4 sine 600 t volts, and remember that 4 is our amplitude of that waveform, and our 600 equals 2 pi times the frequency, and or it equals omega c. So omega c in this is 600, and what is the amplitude of V out? 4. So there we go. We got that one, and then we can solve through for our gain equation. And then we can multiply our gain times our Vn. That's going to be 0.625, because 0.156 times our Vn, which is 4, is going to be 0.625 volts. So now we're going to look at RC as a high-pass filter. And so in this one, we've got our voltage source, we've got our capacitor, and we've got our resistor, and we're looking at our voltage drop over our resistor this time. So we flipped which one we're looking at, the resistor or the capacitor. And now we're going to look at the resistor for the high-pass filter. And so again, we're going to use our voltage divider circuit for resistors that we already learned and swap out those resistors for impedances because it's a little more powerful. And then we're going to put our impedances back in. So our impedance of a resistor is the resistance. So we're going to plug that in for ZR and ZR. And then our impedance of our capacitor is defined by the equation 1 over j omega c. And so we're going to plug that in for our capacitor's impedance. Then we can multiply both by j omega c over j omega c to be able to simplify. And that's going to give us our gain equals j omega RC over 1 over j omega RC. And remember, we have to get rid of that j again. So remember, j is part of the complex number. We can take the square root of a squared plus b squared, and that's going to equal c squared. And then we can also take the phase, which is arctan b over a, which is in the previous slide that we looked at. And by simplifying that out, we're going to get our equation there, 2 pi f rc over the square root of 1 plus 2 pi frc squared. Or you can substitute the 2 pi f for omega, depending on what you're looking for, or given an equation. So here for the high-pass filter, we're going to look at what the cutoff frequency for that high-pass filter is. And so again, we're going to use a very similar equation given and looked at previously, but here we plotted it out to be able to see our gain versus our frequency. So a gain of 1 is almost 100% going through, because remember, a gain, anything times 1 equals like a buffer circuit, it's everything going through. And a gain of like 0.1 is almost nothing. That's 10% of the signal getting 10% getting through. So it's really blocking that out. So now we're going to look at where our cutoff for this is. Cutoff is going to be exactly at the 0.707 because it's going to be determined by the same point that we looked at before, 1 over the square root of 2. And so since this is a high pass filter, all of the values to the right of that are going to be getting through our circuit pretty easily, and all the values to the left are going to be increasingly blocked. So if we look down on the chart, this is still at about the same frequency because we haven't changed the resistor or capacitor from the low pass example. We've kept them the same. We've just looked now at the voltage drop over the resistor versus the voltage drop over the capacitor. And so this gain of 0.7 is going to be essentially the inflection point, the starting point that we're going to look at, the frequency cutoff point for that high pass filter. And so frequencies above 1,100 are going to attenuate through, and frequencies below that are going to be increasingly blocked. So here again, we have our frequency of our high pass equals 1 over 2 pi RC, and we've plotted the frequency versus the gain in decibels, which remember is non-linear scale. And so this way we can look at what happens. So if we identify the point around 1,100, we can look at the frequency of the cutoff point. And again, this is going to be the -3 decibel cutoff point, the same as when we had the other side of the circuit, the same when we were looking over the capacitor, because we haven't changed the capacitor or the resistor's value. And so we can look at this, and anything below that point, you're going to see attenuation, you're going to see blocking of that signal increasingly. So you're going to see that signal being blocked increasingly so when you get slower and slower in the circuit to slower frequencies and lower frequencies. When you get to higher frequencies, you're going to see that more of that is traveling through, almost 0 decibel reduction at around 10,000 hertz. So that's a great way of seeing the high-pass filter be incorporated. So here we have the example for a high-pass RC filter, which is going to be very similar to our low-pass example with a few changes. So if there is a high-pass RC filter where the resistance equals 50 kiloohms and the capacitance equals 4 nanofarads, what is the cutoff frequency omega c? And so we can plug in our omega equation. Omega c equals 1 over RC, and we can multiply 50k times 0.4, and we can grab that out. So actually that number does not look correct. I have to update that in the next version. So here we have our gain of the filter at WC, and we can look at that. So this is the same equation numbers that we had before. And so this is going to be 1 over square root of 2, so 0.707, and then our gain in decibels equals minus 0.3. So this is the same as the low pass. This is just a standardized value there. So now we're going to look at this gain of this filter, which we just looked at briefly, and now we're going to look at the total gain. So the total gain equals gain omega RC over the square root of 1 plus omega RC squared, and then we can start plugging values in for that in order to solve our gain coming out of this. So our gain is 0.477, or again 7 decibels, and solving through again for an input of V in equals 20 sine 2500t. What is the amplitude of the output? And that V in equals our V in times V out. So we're going to look at our gain multiplied by our V in, and that's going to give us our gain of 0.477 times the 20, and that's going to bring us down to around 9 volts. Another example for the high pass filter, we got another resistor value and another capacitor. We've got our Vin equation here, so 3.7 is our amplitude of the wave, our sine 2 pi 60 is our frequency, t volts. What is our omega c? So our omega c equals 2 pi 60, and our amplitude is 3.7. And so if we want to calculate out our omega c, it's 1 over rc. We can get how many rads per second that we have. And then finally, we can calculate out our gain for this circuit. Our gain is going to be 0.0563, so very, very small. And so this is going to give us our input multiply our Vin times our gain. And that's going to give us our V out, which is going to be 2.208 volts. So if you asked how these numbers were generated, we can use Excel to generate these. And this slide kind of details the process there of generating them for different frequencies. So frequencies are plugged in the F category. Our gain is plugged in to the middle one, and our decibel level of gain is plugged into our right. And this is pretty standard. You can look up this online or ask more questions about this in class if you want to calculate these out in Excel. So again, this is another more detailed part of how we get our low pass and our high pass frequency. So with this, you can plug in values if you have a calculator essentially set up for this. You can plug in resistor values to be able to tune your circuit to get that perfect combination of resistor and capacitor to get the end frequency. So next we're going to look at inductors. And inductors, we have our Vin. We're going to use that same voltage divider model because it works really well. And we have our a resistor and then an inductor after it. So for our voltage divider model, our impedance is going to be equal to R resistance for the top one. And then for our inductor, it's going to be J omega L for the impedance of the inductor. Likewise, we could switch them around again to put the inductor first and take it over the resistor as well. So if we look at the high-pass version, we're going to have plug and chug our resistance for our impedance 1. We're going to plug in J omega L for our impedance 2. And then we are going to solve those out to get our gain equation. And then for the low pass, again, we're going to switch the two. So the low pass one, we're going to do J omega L for RZ1, and then R for RZ2. So the first equation corresponds to the left-hand diagram, and the second equation corresponds to the right-hand diagram. The first one is a high-pass filter for an inductor, and the second one is a low-pass filter for an inductor. And so finally, we can substitute out to find our omega c and our cutoff frequency. And those are going to be defined by the two equations in the bottom. So finally, we have our more interesting circuits, which are bandpass and bandstop or notch filters. So bandpass is probably the most useful filter. And the bandpass is a combination of two. It essentially blocks out low frequencies. It lets some middle frequencies through that we really want to look at, and then it blocks out some high frequencies. And the bandpass filter is probably the most useful filter because usually you're looking at a set frequency range. So for MRIs, you're looking at a frequency of around 128 megahertz because that's the oscillation or Lamar frequency of water. So I want to include most frequencies right around that range, but anything way above there I want to block out, and anything way below there I want to block out. And that's how we do it with the bandpass filter. Band stop filters are a little less found in industry, but sometimes they are an important part. So a band stop filter or a notch filter allows low frequencies through, will remove a middle selected frequency, and then allow high frequencies through again. So this one is specifically if there is a kind of a specific bit of noise in the room at a specific frequency that you don't want impeding some other electronics, and you want to listen to the other electronics. You use a notch filter. So sometimes this is for when you're trying to make sensors to analyze ambient data. So a couple other notes about filtering. These filters are not brick walls. They are single pole filters. And what that means is that it doesn't immediately stop at that selected cutoff frequency. You're not immediately shutting everything for a low pass filter. Anything above that 0.707 immediately shut off. It allows some of them through, and even at the lower frequencies, you still have some smoothing of those curves. So they're not perfect filters. And the second thing here we have, they roll off gradually across frequency and only reduce to 0.7% of maximum or 3 decibels at the cutoff frequency. So again, that's just reiterating what I just said, saying that they're not perfect cutoffs. You're not all of a sudden at a low pass cutting everything off at that magic inflection point. You are increasingly cutting more off. So if your inflection point is supposed to be, I don't know, if your cutoff frequency is at 1 kilohertz, and you're looking at 10,000 megahertz of a signal, yeah, you'll probably cut off almost all of that signal. But still, there is an absolute tiny, tiny amount that gets through. And so you just have to keep that in mind. This isn't a perfect filtering. It's smoothing. And so to get a good reduction, your filter should be set at the frequency where your noise will be greatly reduced. So again, the whole point of filter is to remove noise. So you find the frequencies that get rid of the noise the best. Um, Alternatively, we can use multi-pole filters, but these are more complicated, and we're not going to look at them for a little while. So right now, look at these single-pole filters, and usually single-pole are a really nice, easy way to get some good smoothing so you can do some signal analysis or get a cleaner signal in that you can work with. So now we're going to look at active filters. So previously in this presentation, we looked at passive filters, and that means they require no power to operate. That capacitor and a resistor, an RC or an RL circuit are essentially all passive components, so they suck power out of the system. They're not providing power to it, and they create filtering through that, taking power out of the system. However, active filters are powered electronics, and almost always they use operational amplifiers, op amps, to be able to do this filtering job that they're supposed to do. And in general, just as a rule of thumb, generally active filters give you a little bit more smoothing and a little more control over your smoothing, but they're also a little more complex to implement. So you got to keep that in mind too for your design decisions. Again, we have our operational amp or op amp here, and we've chatted about this a lot in chapter 4. So this is an LM741, which is a standardized op amp. We have a couple others that I recommend. The MCP6004 is another good one that we have a lot of. There's a whole lot of different op amps. You got to make sure that when you're selecting an op amp for the job, that you read the data sheets for that op amp, because the data sheets are going to determine different properties of the op amp that are important. So for instance, some op amps have a very set operating voltage range. So, for instance, the MCP6004 only operates at a maximum value of 7 volts between the low end and the high end. So if you try to do minus 15 volts to a positive 15 volts on it, you're not going to get your ideal signal out. Matter of fact, you could blow your op amp pretty quickly. The MCP, the 741s, the LM741s, have a higher range for that. Usually they are, I believe they're minus 15 to 15, although again, you're going to want to look at the data sheet for that. Also important about the op amps is so your total range that they have, the amount of power that they consume can also be important. The signal out and where that comes, you can look at the graphs of how that's developed. Again, they're all going to function under the same gain equations that we used previously and looked at, but some of them have different other properties, so low current op amps, high current op amps, etc., that make those op amps unique and sometimes more expensive and more worthwhile for different applications. So again, what I'm saying with this is when you're using op amps for filtering, make sure you match the right op amp to the right filter job. So here we have an op amp version of an active low-pass filter. So you're going to see it's actually very similar to what we did previously. We're going to have our op amp in there, which is just going to be an inverting signal op amp. And then we're going to put a capacitor in parallel with that R2 resistor. And for equations of this, we're going to look at our gain equation. So remember, we're still going to use our impedance between the two to get our gain, our V out over V in. So we're looking at the impedance between Z2 and Z1. And that's going to be our impedance here, which Z2 equals the impedance of R2 in parallel with C. And we can use that same equation that we looked at before for the voltage divider of two pieces in parallel. And so that's going to be the two multiplied by each other, the impedance of the two multiplied by each other, divided by the sum of the two impedances. And now we can plug in our equations that we looked at in the previous slides today in order to get that and calculate out our impedance 2. So again, our impedance 2 is going to be equal to our gain here is going to be equal to the sum of the two, our impedance 2 over our impedance 1. And this is the algebra for that in order to plug through. You can follow through to see that our gain at the end is going to equal the negative resistance 1 over resistance 2 over resistance 1, negative because it's an inverting op amp, a resistor 2 over resistor 1 because that's normal op amp parameter. And then we're also going to have our equation under here, the square root of 1 plus omega r2c squared, which again, that shows our c value from before where you have c squared equals the square root of a squared plus b squared in order to get rid of that omega. And so the frequency dependent part of this is identical to the derived for the passive low filter theory. And therefore the corner frequency or the cutoff frequency is the same. And we have our omega low pass equals 1 over the R2C, or our frequency low pass equals 1 over 2 pi R2C. And so we can look at our cutoff frequency next for a given case where R equals 1 kilo ohm, R2 equals 2 kilo ohms, and our capacity equals 0.2 mu farad. And if you substitute that all out just to check it out, you should get a cutoff frequency of 398 hertz. So that's just plugging those numbers into that higher equation and solving. So here in this example, we're going to have our configuration for an active high-pass filter. So you can see the difference between the active low-pass and the active high-pass is where we put that capacitor. In the low-pass, we put the capacitor in parallel with R2. And the high-pass filter, we're going to put that capacitor in series with our R1. And so this is going to be our configuration to be able to calculate out our active high-pass filter. And so, again, we're going to use our gain equation, which is the same that we used before. Gain equals minus Z2 over Z1 plus Z capacitor, so 3 impedances there. And then you could start plugging in. Our Z2 is just going to be our resistance 2. Our Z1 is just going to be our resistance 1. And our capacitor is going to be 1 over J omega C. And we can substitute that out. And if you look at the very end, your absolute value is going to be negative R2 over R1. Again, negative because it's an inverting amplifier configuration. And then we have our, essentially our smoothing signal over there with our omega R1C over the square root of 1 omega R1C squared. And so again, the frequency dependent part of this is identical to the derived for the passive high pass filter. And therefore, we can use omega high pass equals 1 over R1C. Or the equal equation, because omega can be 2 pi f, we can just substitute that in algebraically, where the frequency of the high pass equals 1 over 2 pi R1C. And so for another example down here, we're going to look at R1 equals 10 kilo ohms, R2 equals 20 kilo ohms, and our capacitor equals 5 nanofarads. And we can go up to that top equation for gain and plug and chug these in to be able to find a frequency of 3,183 hertz as our cutoff frequency. So again, all we plugged in, if we look at that frequency, high pass frequency, we can plug these in to find our cutoff frequency like we did in the earlier slides. So now we get to the band pass, which is really the most useful and most fun of the circuits. And you're going to see for the band pass, we are going to cut off the low frequencies with that capacitor 2 value, which is in parallel with our resistor. And we're also going to cut off some of the high frequencies with that capacitor 1 in series with the R1. And so for this, we should be able to solve through to find the two values. So again, all we're doing is using those same two equations in order to solve to find our low pass frequency and our high pass frequency. And what this means is that the good frequencies that we want are going to be somewhere within the range of 106 hertz to 2,600 hertz. In that range, we're good. Outside of that range, we're going to be cutting them off increasingly. So there's our two equations as well for your frequency for the low pass and the frequency of the high pass. So throughout this presentation, you've heard me mention the words amplification and attenuation a couple of times. So I just wanted to clear up what that meant. And so in general, amplification, positive amplification is when your gain is greater than 1, and positive attenuation is when your gain is less than 1. So you can also have negative amplification and partial, like essentially you could have other ways of wording this in order to get to the same thing. But when you're talking about amplification or attenuation, you're talking about your gain. And again, amplifying means to make bigger, so your gain is bigger than 1, and attenuate means to capture some of that signal, to weaken it, and that's why our gain is less than 1. And so if you look at a resistor and a voltage source, a simple resistor and voltage source circuit, you can see that the gain is going to be essentially less than 1 because you're going to attenuate some of that through the resistor. The resistor is going to get hot and lose some of that energy. So again, we have our V in as a signal. Here we have an op amp with our gain, and then we have our V out, which is our gain times our V in. And so gain is the ratio of output over input. We've defined this multiple times throughout this course, but gain equals output over input. And so if our signal V in equals 0.01 volts and our V out equals 10 volts, we can see that our gain is going to be 1,000 because you're going to multiply that V in by a gain of 1,000 to get the 10 volts out. So if I have a very small signal, I don't know, coming from a muscle, and that signal is 0.01, or a head jack on an iPod, and that I'm getting a signal of around 0.01 volts, and I want to make it up to 10 volts so my speaker can look at it, I'm going to have an op amp with a gain of 1,000. Likewise, this works for more complex signals too. So if I have 0.05 as my amplitude, and I'm going to try to get an amplitude of 10, I can look at a gain of 200 because 0.05 times 200 equals 10. And so this works for more complex signals as well. So for signal conditioning amplification, again, we're going to use our op amps, our VT, which is our input signal, and then we can have our op amp to make the gain, and then we're going to have our out, which is our gain times our V in, and that's going to be our V out. So again, we're going to look at this from a negative to positive side. And this we've already talked about a lot in the op amps lecture. The two different parts again of the op amp, we have our inverting lead and we have our non-inverting lead, and that's going to bring us to our output lead. And the op amp is going to produce that positive gain for us. And so inside the op amp, like we've talked about before, there's many transistors and resistors. We're going to use the simplified model for any op amp analysis that we do in this course. Again, we've seen this slide previously. The important part that I want to look at here, though, is now that we've looked a little bit about signal analysis, you can see that there's a couple capacitors in there, as well as the transistors and resistors. And so those capacitors are doing some interesting things, most likely in smoothing some signals inside of the internal op amp. So again, we don't usually have to look at this in this level of circuit details, but it's good to know that in the 741, there's 20 transistors, 11 resistors, and a capacitor. So we're going to look at another couple pieces of op amps just to review through them again. So we have, in this case, a signal transmission by differential pair. So this is an interesting one where two wires transmit the signal, where one carries the positive V over T and the other carries the negative V over T. And why do we do this? Well, this is going to give us a cleaner signal. Differential pairs essentially allow your signal to travel further without getting messed up. And so this is one of the interesting parts and uses of signal transmission. So some other op amp concepts that we touched on before. So op amps can be a very, very simple amplifiers. So we have two inputs. We have our voltage minus and our voltage positive, and we have our one output, our V out. And so our output is proportional to the difference between the two inputs. So the op amp is always trying to look at the difference, and if it's different, it's going to try to make it so it's not different anymore. And so we've got a gain internal of that op amp, which is extremely large. So if a gain that large essentially means if there's any noise or any difference between them whatsoever, it's going to send all of that current, all of the voltage on the V out. So this isn't a very useful signal except if you're comparing two things together or comparing if something is on or off. And even with that, it's a very noisy signal because if any time it goes up or above, it's going to turn a signal on or off because our gain is so very high. So how do we work with gains that are this high? Usually we include a feedback source so that we don't saturate the output. So A feedback source allows us to say a lot lower than that K value, which is that ultimate gain. So we're trying to stay with a smaller gain because that way we can work with it. We can use it and process it a little bit cleaner than if we just throw all of our power on or all of our power off. Again, we've looked at this slide previously. We're going to look at rules for solving an ideal op-amp circuit. Again, the voltage at the two terminals are always equal. No voltage goes through the positive or negative inverting terminals. And then your output voltage will change in order to keep 1 and 2 true. So we can look at this again in a couple hand problems. Again, the simplest concept, and we've looked at this one multiple times in class, is a buffer circuit. A buffer circuit has a gain of 1. There is no gain. So it's essentially a single gain. It's whatever this Vin equals is what comes out. So whatever signal comes in, the exact same signal comes out of it. Why is it useful? Because it helps protect circuits. So our Vin equals V out. However, since no current is going in or out of that negative terminal on that op amp, we've protected that circuit to allow it some buffer protection in case some accident happens later in the circuit. Here we have our inverting amplifier. And in our inverting amplifier, we're going to send out the exact opposite of the signal that is coming in. So V in and V out. If V in is a positive sine wave, V out is going to be a negative sine wave. And it's going to be amplified by whatever the value between those resistors are. So if we do a nodal analysis of this, we can see our V out over 2 equals our negative V in over R1. And our V out over our V in equals minus R2 over R1. So our nodal analysis allows us to create the amplification factor, the gain factor. So if we want a really small gain, so something extremely negative, we have our larger R2 value than we have our R1. Our R2 can be 1,000 ohms, and our R1 can be 10 ohms. Then we'd have a very significant negative gain factor. So that's how we calculate our gain, and that's how we calculate our V out, because our V out is going to be whatever the gain is times our V in. For our inverting amplifier, if we have these two values, R1 and R2, so this is similar to what I just said, we're going to be able to calculate out what our gain is and also what our signal out is. So our gain is going to be our 2,000 over 100 negative because it's inverting. And that's going to give us a gain of minus 20, which is decreasing, essentially. You're having the waveform go in the negative direction. Another inverting amp, if we have our R1, our R2, our Vin equals 0.8, what is our V out? So again, you're going to be able to do, it's an inverting amplifier, so we can do our R2 over R1, our negative equals our gain, and then we're going to multiply that by our 0.8. So our negative R2 over R1, and then multiplied by we can go. So an adder op amp allows us to add different numbers. So we can look at our nodal analysis at the different points of this to be able to generate our equations for adding signals together. So our V out equals our negative RF of V1 over R1 plus V2 over R2. So if we pick R1 equals R2 equals RF, and that's just for this equation, that's saying that our three resistors are the same, we can get our V out equals our V1 plus our V2. So that's essentially saying it's the same, the two R1 and the V1 and V2 are weighted the same way, and they're just added up. So for more complex adder circuits, you can add as many as you want. Every time you're going to add them, you're going to add the voltage of the new one divided by the resistance of the new signal. And so we can have one example here that you can solve out, which you'll see we're going to get a signal V out of minus 5.13 volts. Non-inverting amplifiers are going to keep things in the positive direction. So again, that's where the signal is going into that positive terminal on the op amp. Non-inverting amplifiers function very similar to inverting amplifiers, except a slight twist on the numbers, which we're going to look at now. So if we do our nodal analysis at node A, you're going to see that V in over R1 minus V out minus V in over R2 equals 0. We can use a little algebra to be able to simplify that out to our V out over R2. And so V out is going to be the sum of 1 plus R2 over R1 times the V in, where 1 plus R2 over R1 is the gain function there. And our Vn is going to be whatever is given to us in the Vn. So we can multiply the Vn by the gain to get our V out. Here we have, again, R2 and R1. So how are we going to solve this? Well, we're going to plug it in the previous equation that we had. So our V out is going to be equal to our equation for gain times V in. And if you look at that, you're going to get a gain of, what is that? A gain of 21. So 21 V in. And that's exactly how we solve for our gain. So the non-inverting amplifier, the key feature is that the input goes straight into the non-inverting lead. And so on the right, we can see two different images. So in that top one, we have a circuit where the feedback loop is going directly into that non-inverting lead, into the inverting lead, and we have an equivalent circuit for that one as well, which the equivalent circuit for those, it shows that R1 shifted up because essentially it doesn't really matter where it falls on that line. So again, we have a couple other examples for our non-inverting amplifiers here. Connect VP to input signal. We connect our VM to our voltage divider between 0 and V out. Our gain is the ratio of V out to V in. RA equals 6.8 kiloohms, RM equals 56 kiloohms, and our V in equals 0.56 ohms. So we can plug these equations in to get the answer for this non-inverting amplifier. Plug and chug to get our gain, and then multiply our gain by our V in to get our V out. The difference amplifier computes the difference between two signals, and again, this is often used in biomedical engineering because it's a great way to remove noise out of a signal, actively move noise out of a signal. And so our equations for gain are slightly different. We have here our V out equals our R2 over R1 VB minus VA. And this is saying that R1 is equal on both and R2 is equal on both. And that creates the difference between the two. So again, same equation as before, except for R1 and R2, we've substituted in RIs and RFs. So I'd like you to solve this one now, pause the video, and let's see if you get the solution correct. So you should have found the solution now and unpause the video, and we're going to look at what the answer is. Our gain equals 3.73 because 8,200 divided by 2,200. And our V out is going to be our gain multiplied by our difference between our V ins. What's that? So again, our key ideas for op amps that they're low power device, 10 milliamps, 12 volts. Our output is is a difference between two inputs, and it's multiplied by a big number, which is our gain. And that's usually why we use a feedback loop, because our gain is so big it's not useful. So we send some of it feedback to make it a little more insensitive to K. So op amps, active filter op amps, and op amps are useful for adding signals, subtracting signals, scaling, and building filters. Here we're going to go through a couple different exercises. I'll let you pause the video at your own leisure so that you can see and solve these problems. So here we got our exercise 1. What is the gain? Pause now. Unpause. The gain for this circuit is negative 21. Exercise 2. Solve this circuit. Pause now. Unpause this circuit. So in this, we're going to be able to solve what other resistors we need, what the circuit will look like. And so we have our two inverting gains here for our solutions. Here we have exercise 3, and we're going to look at what the gain is. And so this is going to use that one slide in that we looked at a couple before, that's to be able to transform this op amp into one that we look at, because it is not a buffer op amp. So what is the gain to this circuit? Pause now. Unpause. The gain to this circuit is 4. In example 4 here, we want to build an amplifier with a gain of 9.1, and we have a 2.7 kilo ohm resistor. So what other resistor do we need, and what will the circuit look like? Try to draw it and calculate out what the other resistor is, and pause now so that you can do that, and then we'll restart it in a minute. So pause now. Unpause. If we look at our gain for 9.1, we're going to be able to back solve to get a resistor value of 22,000 ohms. And alternatively, we could get another solution, which is 330 ohms, depending. So in example 5 here, we're going to find the input-output relationship. So first, identify what kind of op-amp this is, and then solve for the gain of that op-amp to identify the relationship between the input and output. So go ahead and do that now. Pause now. Unpause. So if you calculated this out properly, our V out equals minus 18,018 kilo ohms times the sum of V1 over 3,300 ohms plus V2 over 6,800 ohms. And so that's going to give us our equation there if we multiplied it out by minus 5.5 V1 minus 2.6 V2. So finally, we're going to review this, and we've used this slide a couple of times now, but complete this slide on your own. See if you got it correct, if you've identified the correct op amps. That's the first step. And then if you identified the correct op amps, that you have created the correct gains for them. So one other thing I'll notice in this one, that in the inverting slide, that should be gain equals minus R2 divided by R1. There's a negative sign in there. Just making sure that it's there. So pause now and solve. Check your solutions for this one. Gain of 5. Gain of 4 times 0.2. Our V out equals 2. We have our V out equals 4. We have our V out equals 8. So we have those as answers there. Finally, here we have another review that we're going to have to identify. So use your notes to answer these, and or in preferable, use your note sheet that you're going to use on the test. And therefore, you can see if your note sheet is added up correctly. So match the statements to the left to the following for gains and equations. Pause now. Unpause. Let's see how you did. If there are any questions with those, feel free to ask me during office hours.